Okay. Good morning, everyone.
Yeah, good morning.
I guess we should, go ahead and start. And there are quite a few people registered for the course. About maybe 2/3 of you are here now, so there may be some more people coming in a little while. So you might have to get a little bit cozier than maybe you're comfortable with. But so welcome to the, combination of the Introduction to Quantitative Geology and Automating GIS Processes courses. If it's just occurring to you now, we have two courses that are meeting together in this room during period one. And my name is Dave, and I'm the lecturer for the Quantitative Geology part of the course.
Yeah, and my name is Henrik, and I'm the lecturer for the Automating GIS Processes course.
And we have a few other people here that maybe we'll just quickly introduce you to. There's the two ladies sitting up front here. And you can tell them your name if you like.
Hey, so my name is Wolfo. I'm the assistant, later for the Automating GIS Processes course, but in the first period for the Geo-Python part. I'm a doctoral student here at the department. I use Python almost every day. I hope to get excited about programming it and to make your lives easier after taking this course. Welcome. Yeah, hi, I'm Jolina, and I'm pairing up with the Quantitative Geology course, and I don't use Python every day, but I will try my very best.
And then we have the two guys up front here.
Hello everyone, my name is Samuli. I'm a master's student here, and I use GIS and Python in my work and also in my studies here. I did this course last year. I enjoyed it very much. I hope you enjoy it as well, and I hope you learn as much as I did.
Hello, I'm Antti. I have similar background to Samuel, but I don't use Python every day. But yeah, we'll all get better.
So we'll meet you mainly on Thursdays and Fridays in the practical sessions in physics.
Yeah. So that's kind of who we are, and
Maybe we didn't say who we are.
well,
too much.
not in so much detail.
So a little bit of my background. So I'm a PhD student as well, defending this autumn. So it will maybe affect a little bit about all the GIS course stuff, but not too much, I hope. And I'm part of this digital geography lab where we do quite a lot of stuff using Python programming, and I've done that since 2012. I started during my master's thesis and now do it basically every day, and it's fun.
And I guess just to give more background to me, I'm an associate professor of geodynamic modeling, so I'm a little bit outside the realm of GIS kind of stuff. And I learned to program mainly using Fortran, and would not really like to inflict that upon any of you. So that's why we're learning Python here. It's a lot easier to learn. It's a lot easier to play with, and I would say the majority of people who are doing programming in natural sciences today are moving the direction of things like Python rather than Fortran. Fortran is kind of nasty. So so we've got some course websites. I guess you've probably been to one, maybe several of these, is that right? You found some of the information online. We're going to more or less keep everything in the course on one of these websites. For the first period, we're going to have everything in the Geo-Python website because we're both here to learn Python together for the two courses. So we're not going to use Moodle. That's maybe an important thing to know. You will find that there is a Moodle page for the course from last year, but we're basically not going to put anything on there. And in fact, maybe we'll just hide everything that's there now so that you don't get confused. But everything's going to go on one of these sites. In period one, it'll be the top one, and in period two, it'll be the site that's relevant for the course that you're enrolled in. And I don't know. Henrik, do you have anything to note about the AutoGIS course?
No, I guess not.
Okay. So that brings me here, and I'll start with a little bit of an apology. For those of you who are taking the Introduction to Quantitative Geology course, I realize that registration in WebAudit is not at all clear, and I don't personally want to take the blame for that, because we've switched to this new system for how you sign up for courses this year, and it just turned out to be kind of messy. But if you're taking the Intro QG course, basically you should tick all of the little boxes when you register for the course. Even though it says something like, automated GIS processes lectures, or automating GIS processes, how do you like this, like the exercises, you should just sign up for all of the options, because for some reason in the system it was only able to list one course title, even so, like we're both meeting in this room and it listed as automating GIS processes for period 1. I don't know why, but that's how it works. And so
basically it doesn't matter because we are all kind of mixing here. So although the Thursday exercise group is basically for all the GIS course and the Friday is for Intro to Quantitative Geology, you can choose whatever group you want because we are basically doing the same stuff, so it doesn't matter at all.
Yeah. So the one thing I'd also like to note is there is this option for the Introduction to Quantitative Geology course, since it's a bachelor's level course. If you want to get 2 credit points of your English language proficiency satisfied in the course, you can do that by registering for the part that's listed as academic and professional communication in English. In period 2, there'll be a few meetings with someone from the language services who will give you some basic instruction about writing in English and communication in English, for those of you who would like to take care of some of those credit points. If this is confusing at all, please talk to us at the break or after class, and we'll clear things up. I just realized that one thing I did want to do here was just show you the website, because even though most of you have been there, there is a bit of useful information here in the general info section, just to be absolutely sure you know what's going on. We're meeting in this room on Wednesdays 9 to 12 during period 1. We have 2 work sessions where you can come and work on the exercises that we will introduce during the lecture time on Wednesdays, and they're on Thursday from noon to 4 and on Friday from 10 until 2. You can come to either one. It doesn't matter.
No, I guess we hope that so that everyone wouldn't come on Thursdays or Fridays, so that because we have the GIS lab, so there's basically computers for 24 students, and then I think, most of you have your own laptop, so it should be okay. But still, the room is for 24 students, and of course we have the hallway where people can sit on those chairs, but if we have 80 people on the same day, we're gonna have some trouble there.
Yeah.
Maybe coming to that, but how do we return the exercises, and do we have to go to the exercises?
Yeah, so good question. We are going to use, we'll really get into it next week, but we're going to use a system where you will submit your exercises and things like that electronically through a web page.
We will go through the process already today, kind of give the principles how to do that.
So, and no, you don't have to come to the exercise sessions at all. In fact, maybe one thing we could note now is we are recording this lecture, at least like this area of the lecture room is being recorded. We're just testing it out, so this might not work, but we're hoping to be able to put the lectures up on the course webpage after class each time, so that even if there are some mornings where you're not able to be here, you might be able to catch the lectures online. But I will give you a word of warning that I don't want to have a situation where 2 students show up because everyone's like, oh, I can just watch it online, man. So
we can
please come and make us feel like we're here for a reason, because we want to we're trying to share what we do in the course with a broader group by making the webpage videos and things like that available to you all. But it is also nice to actually see people sitting in the seats in front of us. So anyway, just other thing to note on here, all our contact info for the instructors is on the website. More of the web pages and things that we'll use are listed here. We'll talk about that stuff later. But I just wanted to make sure that you kind of knew where to find some of that.
On Webody was written that on Thursdays in Finnish and on Fridays in English.
Yeah.
Both English or?
All the course, so the lectures and exercises, they are all in English. So that's mainly because I'm like a Finnish person and I have all the GIS, so I guess the language came from that. And because you're from US, so yeah, it was in English, but it doesn't matter. We have all the materials and the lectures are in English.
Yeah, and it's also, I had courses that I have this year that were also listed as being given in Finnish language for some reason. This system of setting up the course stuff in WebOD this year has kind of not gone as smoothly as we might have hoped. So, now we can move on to a question for you, and that is who you folks are. In the past, like last year, we kind of went around like each person introduced themselves, and obviously there's a lot of you now, so we're not going to do it that way. We're going to instead use a poll, and if you've got a phone or a computer in front of you, you can go to this webpage, geo-python.github.io/poll, and you should see something that looks like this. And so you can tick one of those boxes, and I guess maybe you want to put up the results.
Yeah.
Page.
Just that, so basically we have these kind of questions. Let's see about the results. Few fancy stuff going on here.
Yeah, we're going to out-technology ourselves here.
All right. And wrong.
So we have
one down tool here as well. Okay. Good. All the GIS, you're active.
We're catching up. So anyway, the point of this question here is basically just to give you some idea that we're about half GIS people, half geoscience types, and one person who's, I guess, straddling the border between the two. Nearly split down the middle. I think there's 38 people registered for both courses right now. And maybe we could just kind of do an informal manual poll of how many are bachelor's students? It should be like a good chunk of the quantitative geology people. Okay, so the people kind of hiding out in the back mainly. And then how many are master's students?
Okay.
And then are there any PhD students? Okay. Well, yeah. So we have a few.
Yeah.
All right. So you got some idea of
yeah, about the polling system. So basically, we are going to ask you questions in using this system. So whenever we say, you just go to the website and then pick up the choices that you want.
Yeah. And maybe we can, on that note, let's learn a little bit more about each other.
Yeah.
We're going to switch questions and switch results. So the question now is, if it shows up.
Yeah.
There you go. So you can choose as many of these options as you like. We just kind of want to get some idea of what type of things do you folks feel like you want to learn in this course.
Okay, good. You want to learn everything. That's nice.
Yeah, I was going to say. So we have a few others. Does anyone want to volunteer what their other types of things might be? Like, does anyone who's put other feel like they have something specific in mind that they might like to learn? Just other stuff.
Yeah. That's okay.
So, yeah, well, you can see obviously not a big surprise that a lot of you are interested in learning to program in Python. That is, we've got a pop-up here. That's a big part of what we're going to do, especially in the first part of the course. But
we go to the next one.
Yeah, let's just automating research tasks. I think Henrique will certainly talk a bit about that. We'll do some of it in the quantitative geology course, but that's going to be something he'll cover. And
You want to go to the next question?
yeah. So, yeah, now the question is, how much programming experience do you have? And be honest, there's no shame in saying you've not done any programming before. Or if you feel really confident, you can choose the bottom option. Yeah. So we have one programming head. Oh. Like a true programmer, don't hide from the spotlight.
Yeah. Don't be ashamed. You can tell if you're a pro.
But yeah, again, I mean, this is a kind of a useful thing to see that maybe not quite a third of the course are people who've never done any programming before, and that's totally fine. That's kind of, we're going to teach programming in Python from the very basic level. Some of you who've done a little bit of programming but don't use your skills have probably forgotten a lot of what you've learned, and so this will hopefully be useful to revisit those things. And even for those of you who would say, I regularly write my own programs, hopefully you pick up a couple tricks from us.
Yeah.
Because we're going to try and teach you some things that, if you're a self-taught programmer like I am, and Henrique, there's a lot of the stuff you just don't find without looking for it. Like if you just try to figure out how to get a program to work, you can do a lot of dumb things that computer scientists figured out a long time ago are bad ideas, and we're going to try and tell you some of those things to help improve your programming skills. I think we have one more question for now.
So,
and that is, for those of you who've done programming before, which languages have you used?
Okay, so plenty of Java. I guess it's the introduction to programming course at the computer science department. Also some Fortran.
Yeah, we got one bold Fortran programmer out there. Cool. Okay, so yeah, I mean, this is to help us get a sense of who you are, and also maybe help you get a sense of who you collectively are. And there's a bit of programming experience. Some of you even have done a bit of Python, and that's a good thing, because hopefully what it means is, if you look around the room, we've got a wide variety of people with different levels of experience, and we'd like to encourage you, to talk to the person sitting next to you from time to time and take advantage of the fact that someone might know a little bit of Python if you don't know any, or have programmed in Java and at least know some of the concepts of programming as we're learning.
So we are kind of doing a learning experience all together. So also us teachers. So we are again doing experimentation with you. So we don't know exactly how this will go, but anyway. So please talk to each other and ask questions and discuss. So that's how we learn efficiently.
Yeah. Okay. So let's see now. We're going to switch back maybe to here. And just say a little bit about the goals of this first half of the course. If you've read the course webpage, you've probably seen that we're going to try to introduce you a little bit to programming in Python, starting from the beginning, and just give you some basic skills to teach you the main elements of how to write simple programs in Python. And really, it could be any language. We've just chosen Python because it's widely used and it's freely available, unlike things like MATLAB. And yeah, develop basic programming skills. We're going to talk a little bit about the core concepts of what is a program and what are the sort of logical things you have to do when you write any kind of software. And hopefully by the end of this first 7 weeks, you'll at least have a picture in your head of like when we talk about something like a loop or some kind of logical statement or an array, that you have something kind of comes to mind and you have some picture that will help you in understanding not only the programs that you'll write as part of the course, but maybe if you go online and find other programs, you can start to kind of pick apart what the code is doing.
Yeah, it's really nice when you kind of start seeing that, okay, I didn't know anything about programming, and it has been like Hebrew when you see some piece of code and when you suddenly start to actually realize that what is happening. So it's a nice feeling.
And along the way, we'll talk about some kind of good programming practices. And at this point, if I can change out of here, I'm going to pull up the course webpage again, and maybe I'll just enlarge it just a little bit. To give you a little bit of motivation for the course, probably some of you don't need this, but we kind of thought this would be maybe helpful just to get a picture of what types of things we're going to do. You can read the webpage at home, but I'm going to give you the kind of short version of what this is. And that is basically that we have a number of things we're going to talk about in the course, about how to write software, how to keep track of the changes you make when you're writing your software, so that if you make a mistake, you can go back to a version of some software that was working before, how to make programs that are easy to understand from the perspective of a person, not necessarily from the perspective of a computer, but that you can share your software and a person can look at it and figure out what it does pretty easily. There are some very useful things that are small things you can incorporate in your program that can really make a big difference in terms of how easily it is shared. And the last point here is about producing kind of simple data visualizations. So we'll do some plotting in Python at the end of the first 7 weeks, and you'll continue on with it in period 2. And so this kind of brings up the general topic of data visualization. And if we look at most of the things we're going to end up plotting in any programming language, but something like Python, it looks kind of like this. And well, as you can see sitting there in the audience, I don't think anybody has any idea what this data is in this form. You might be able to, if you're sort of a GIS type, go like, oh, minus 999, that must be, or minus 9999, that must be no data, or something like that. But otherwise, nobody really knows what the data is when it's in this form, but this is the form in which we receive data in most cases. And it's not particularly interesting, it's not particularly illustrative, it doesn't illustrate what the data shows very well, but you can take the same data set and make a plot like this. So now we can see a little bit of what we're looking at, and this is variations in mean annual temperature, and it's sort of an anomaly, so it's a deviation from some mean value, so positive or negative anomaly compared to some mean temperature. And you can see in this case a time scale that goes from 1880 until I think 2011 in this plot. And nicely see trends like since the mid-1970s, global temperatures on average have gone up fairly rapidly to maybe 0.6 degrees C higher on average than the period, I think from 1900 to 2000 is the average for the anomaly. So this is one way in which we can visualize data. We can make plots like this in Python, and in fact, you'll make some plots that look sort of like this when we learn how to do our plotting in Python. And there's quite a bit of information from that data set that we just looked at that's shown here in a much more intuitive way. So this is good, but maybe some of the geography-minded people are sitting there saying, well, that's cool, but the data set we have has geographic information, and that's kind of lost in an XY plot. So you can look at the data a different way, like this, and I'm sorry I've kind of cut the scale off at the bottom. That's, again, temperature anomalies going from -5 to +5. And this is the temperature anomaly in 1 month. So if you're wondering why the scale is so much broader than it was before, you only have 1 month of data that you're calculating your anomaly for, rather than calculating it for the full year. Anyway, the point here, of course, is that now we can see in a spatial context the same type of data. So we can see on a map, you know, let's look at, I don't know, North America, for instance, and you can see that in much North America you're in the red, which means temperatures on average are higher than they were. Same thing goes for Australia, but you go to South America and you see kind of a different pattern. There's more data, well, not necessarily more data here, same data, but it's just displayed in a way that now gives you more about the kind of geographic context of the same data set. And at least in the automating GIS processes course, you're going to do some kind of work with proper GIS
we are doing
data files.
Yeah, we are doing basic mapping and doing maps in the later part of the course. So we will learn how to do these.
Yeah. So we'll learn things like that. And does anyone want to venture a guess on what's the deficiency in this kind of plot? What's missing here that we had in the previous plot? Because we're missing one important thing. We now see the data spatially. What's missing? Time, yeah? So, right, we have a single snapshot in time. We have a nice map pattern, but a single snapshot in time. And it turns out you have to be pretty clever to come up with good ways to visualize data that varies in space and time. And, well, perhaps some of you have seen this video. Yeah? Has anybody seen this? It sort of went viral, I don't know, maybe a month or two ago. So this guy at the FMI, the Meteorological Institute, put together a really nice visualization showing, again, temperature anomalies through time, and now it's broken down into this kind of interesting radial plot, dividing things into different continents and different countries. So we have a tremendous amount of information here, and in this case it's an animation, so if you haven't seen this, we'll click the play button down here, or at least try to click the play button. And now you can watch and see not only how the temperature anomalies vary in space, but also how they vary in time. And you can see broader patterns too from the color scale, that as you start to get into the 70s, you start to see more of these kind of reds and yellows. And clearly you can see a lot of the trends that we saw in the first plot of the average increase in temperature. We move into a lot of the red colors here. We see the spatial data, and we see the variation in time. Now, this is a nice example because the code for making this plot is available online. It's a Python code, and it's actually not really that complicated. It's, I don't know, maybe 300 or 400 lines total, if even that. Yeah. And a big part of that is actually some data that's pasted at the top of the file to show you one example of how the data works. But this is kind of here to give us a little bit of inspiration, because toward the end of the course we're going to do plotting. We may even do some of these kinds of animations, maybe not quite of this scale and caliber, because this does take quite a while to set up the visualization. But you know, if you're interested and curious, you can start with something that produces this plot now, and with your Python skills you'll have in about 7 weeks, you can start tinkering with things, and maybe you come up with an even better way, and you could be the next kind of Twitter superstar or something like that. Yeah. So I know we all aspire to.
Yeah, basically we are using the data that he has used for this, producing this plot or an animation. So basically we are working towards this. Yeah, we're not sure if we're gonna get there. I guess not, but basically the idea is that when you proceed and learn more, you can at one point come back and actually do this plot yourself.
And yeah, at some point later in the course, we'll put the code on one of the web pages so that you can at least download a copy and take a look. The guy's name, I think, is Antti Lipponen, who's at FMI in Kuopio, we might think. Yeah. So anyway, he's very nicely provided his code freely available, as long as you follow the license, which basically says, you know, just don't take it and pretend like you made this yourself, but make sure that you give him credit. So here we are giving him credit. And yeah, So I'm sure you're all now very inspired, and with that inspiration, we're going to move into the first lecture part of the course. This is really the only kind of proper lecture we'll have in the whole course, I think. But we've got to talk a little bit about what's a computer and what's a program and some basic terminology in order to start any kind of course where you're going to learn a little bit of programming. And so we'll spend a little bit of time here going through some basics about programming computers and things like that, and then we'll take a little break and come back. And by the end of the session this morning, we'll at least do a little bit of Python programming. So we could start with the general goals of the lecture. Well, we want to talk a little bit about basic computing practices and talk about what a computer is and what a programming language is as a way of communicating with the computer, and look at some of the parts of what comprises a computer program. And, well, maybe just to give you some ideas, we know that you're not programmers, but learning to program is a really important skill as young scientists. I'm sure it's very clear to you that a lot of the science that goes on now is increasingly quantitative, and if you're able to put the computer to work to do some of your data processing and things like that, you can save yourself a tremendous amount of stress. So, learning to program is, I'd say it's an essential skill at this point as a young scientist. And, but, we recognize you're not a computer scientist, I'm not a computer scientist, Hendrik is not a computer scientist. I doubt very much that a single person in this room is a computer scientist, although I could be wrong. If so, we're probably going to get embarrassed at some point when they ask us questions we can't understand. But, we think you need to know how to program. And, well, essentially I've already said this point, and that is that science is getting more quantitative. Geosciences in particular are moving away from a period of time where you could just describe the rocks that you encountered and their relationships to one another, and really you're now needing to have laboratory analyses and some kind of simple model that you compare your laboratory analysis to in order to be able to do kind of modern geoscience. And another thing that's kind of nice about learning how to program just in general is it gives you some freedom. It gives you some power and flexibility that you can extend what software that exists can do. So you can take programs like ArcGIS that I'm sure many of you have used. ArcGIS has a built-in Python connection. I don't know exactly what you'd call it, but Python's built in, and you could write simple Python programs that will do processing of things in ArcGIS. And I've written or had a master's student that wrote a little plugin for doing different kinds of processing where you had a little window that would pop up and buttons you could click to process the data that was loaded into Arc. And there's a lot of programs now where they're starting to build in these kind of Python interfaces because it's such a powerful way to be able to extend what the program can do by itself. And so here's just a nice example of the little Python window that you can pop up in ArcGIS. So you could type in commands there, like here, I've typed in hello world or print hello world, and you can do regular Python stuff in there. But you can also load and manipulate your GIS data. And I guess, will you guys do any of that with Arc, or?
I guess we are now moving more to this kind of open source. So last year we did ArcGIS scripting, and the materials are still available from the old pages, but I guess we this year moved to using Quantum GIS to do similar stuff that we did with ArcGIS.
Yeah, okay. And another thing, just in general about why it's worthwhile to learn to program, is it's actually kind of fun. Once you get past the kind of mental block of, I can't figure out how to program, it's too difficult. Well, that's why we're here. We want to help you get past that point of just thinking, it's outside of what you can do. I'm quite convinced that more or less anybody can learn how to program. And you know, there's books like this one here that you know, kids that are 5 to 10 years old are starting to read through and learn basic programming concepts at quite an early age.
Basically nowadays in Finland they start doing programming in 3rd grade. So kids that are 10 years old are really starting to learn.
And you guys aren't old enough yet that you can claim, you know, like, oh, that's, you know, that's for the youngsters. Like, you are the youngsters still, so you can certainly be learning how to program. And you're going to do a lot of stuff as you come to realize that's everyday things, just in a way that you're communicating with the computer rather than maybe communicating with another person, for instance. So it is fun, and I hope that by the end of the course you know, have fun at least at some point with learning how to program. And another thing is, you know, when we look at things like just how we conduct science in general, the scientific method, learning how to program can make you a better scientist. It doesn't automatically make you a better scientist, but it can make you a better scientist. This is the scientific method, and I guess maybe you've seen this before at some point. But this is, you know, if we were to outline how we should ideally be doing science, this is what we should do. So we should, you know, be starting with some kind of question, getting some observations, coming up with some hypothesis for how we think things work, testing it, analyzing the data, etc. Now, by learning how to program, we can improve our ability to do things like gathering information and resources. You can set up a script that will pull down data from some source online and perhaps process it, distill, you know, very large data sets down to something that's much smaller and easier to deal with.
Basically, what we are, for example, doing in our research group is that we collect social media data continuously from different sources. So for that, we are using programming, of course, to connect with the social media platforms.
And you can also do things like perform an experiment and collect data in a reproducible way by writing a program that will allow you to basically repeat your same actions exactly every time you run it. And collecting data, for instance, again, that's something that could be done with a script that's pulling social media data, could be pulling down daily temperature data from the Meteorological Institute, or any number of things.
Open data available, so there are millions of sources.
Yeah.
So the amount of open data in the world has increased tremendously in the last years.
And you know, I think probably point number 5, analyzing the data, is not a surprise. You know, a big part of probably what you picture in your head when you think of what a program should do is processing some data, either converting it from, you know, a table of numbers into a plot that you can understand, or analyzing it in some other way. Obviously, programming can help, and it can help with data interpretation, particularly with things like visualizations and other things related to that. Now, by learning how to program with these sort of quote-unquote good programming practices, we can improve things like making our data reproducible, or making our results reproducible. So, you know, a good example is, I think a lot of people, when they learn how to program, tend to write some little script and then, you know, make a plot, and then continue to modify the script, make other plots. And if you go back in time and someone asks you, you know, well, could you make this plot that you published in the paper 5 years ago? You're left in a situation where you're like, no, because I can't undo the changes I've made to my software. We can teach you some things that will help with that. And, you know, reproducible science is a big part of the kind of open science concept that is something I think certainly within the University of Helsinki has been pretty broadly embraced. Internationally, I think it's an idea that's growing in terms of people's interest in doing quality science, and this can, you know, this is one course where hopefully we can teach you a couple things that will help with that. And the other thing is down here at the bottom, retesting. So if you make your code available to someone else, you could say, hey, yeah, I made this plot, take my code and reproduce my results, go ahead. And that's another important thing, because you'll see, you know, these kind of science scandals every once in a while where someone publishes some fantastic result in Nature and gets, you know, just all the acclaim of the international science community, only to find out later that the results can't be reproduced, and then they start digging in deeper and they find, oh, there's, you know, this doesn't look actually like it's consistent with your data set, and pretty soon someone's lost their job and the university looks horrible and blah, blah, blah. So, you know, we'll help make sure that doesn't happen to you. We can't guarantee it, but we'll help. Okay, so on to our kind of big topics, things like what is a computer, and we're going to crowdsource this one. So I'm going to ask you to go to the same polling page that you went to previously. I guess I copied and pasted in the direct link to it. But if you go to the polling page, and maybe we can put this, is it PC2? Yeah. This is a little bit different kind of poll. So what you can do is you can type in your ideas of what you think a computer is, and people can vote to either, to support, I guess you can't vote against it, but they can vote their support if they agree with what you think a computer is. So, feel free to throw things in there, and feel free then to click on the button if you agree with what has been listed there. I guess there's nothing that prevents you from putting the same thing in twice. So try to take a look at the screen before you hit enter once you've typed something in.
Oh, this is clever.
So yeah, this is a discovery made about midnight last night. I was like, oh, these are cool. So
Okay, let's see if we can fit this to the screen. Good. We have some
excellent emoji choice there.
basic components.
Yeah,
That is great.
well done. So we'll let it go for maybe another minute here with suggestions and things like that.
Friend. It can be.
Yeah, it can be your enemy too. A collection of computer parts. That's a good one. So we're seeing some kind of popular things make their way up to the top, and a machine that processes data. I think that's a pretty good suggestion. Machine to make your work easier. Well, in theory. Data storage, tool, program, calculator. There's a lot of different things that go in here, and yeah, I think we've got a number of the elements. Let's leave that up for just a second. I'll move on to here, which is the computer scientist view of what a computer is. Very simple thing. And I don't know if anybody had anything in here about input and output.
Okay, we have this one here as well. Plenty of times. That's good.
But anyway, when we look at it, yeah, the computer, the essence of the computer is it's something that stores and manipulates information under the control of a changeable program. So when you look at something like calculator, most calculators, other than those that can be programmed like the kind of fancy graphing calculators, most calculators are not really technically a computer because they have a fixed set of operations that is hard-coded into the chip inside the machine, and it really can't be changed. So we can highlight a few things here. If we look at the picture, we have some kind of input device, keyboard, mouse. If it's a tablet, it could just be your finger tapping on the screen. An output device, which again, in the case of a tablet, might be that very same screen, but could be a printer, could be, I don't know, these projectors are output devices. We've got some kind of processing unit, the CPU, so that's going to kind of do some information processing, calculate things, whatever. Some memory in which that information is temporarily stored in and sent back and forth to the CPU, and then secondary memory, which would be things like a hard disk, where you're kind of doing more permanent data storage in some sense. But yeah, manipulates information, so we give some input, type something in, something happens, and it gives us some output. You can, if you take an example like your smartphones are computers. You can talk to it. Like I could ask Siri, where's the closest grocery store, and she'll try and give me some information about that. But I talk to it, that's my input, and it processes my voice, does some kind of calculation, and sends back out some human-sounding thing that hopefully tells me where the nearest grocery store is. And the changeable program part is the other important thing, and obviously, we're going to be writing our own software, our own programs, and those will be freely modified, but that just distinguishes it from things that have like a fixed task, like a calculator, or I don't know, there's lots of other things. Digital scale, for instance, would be something where it's not really a computer. So that's the picture of what a computer is, and the very exciting drawing that a computer scientist has come to mind when they think of a computer. And we can ask the question of, well, what are computers good at? Computers are really good at things that are well-defined, clear tasks that have a nice, exact description. So if you tell the computer, add 2 plus 2, and you do it in a way that the computer understands, like typing it in, and return the answer, you can press 2 plus 2 and hit enter in Python, and you'll see that the number 4 is what it returns. Computers are also good at things like storing and manipulating data. That's not a big surprise. You all have majority of you have a laptop sitting in front of you, and it's going to be storing data as you browse the internet because you're bored of listening to us or whatever. And good at repetitive calculations. Yeah, one of the things we want to teach in programming and just learning to program in general is that you should reuse code that you generate, and computers are very good at doing things like going through and just repeating the same calculation that was done millions of times. That's a very happy computer when you tell it to do the same thing over and over again. People are not, turns out, working the same way. And processing data, yeah, well, we've already kind of covered that stuff. In case you're wondering, this is a little Python prompt, and maybe I'll get this up now on both screens. Just to give you an example, this is, something you can do in Python where you can type in this print function, 2 plus 2, and then if you hit enter, it will show you 4, and things like that. We'll play with that stuff in a little while, but just to kind of show you that there is some Python code here on the screen. Computers aren't good at things that are not well defined or abstract tasks. So if you just tell the computer calculate pi and you don't tell it how to do that, it's not going to do very well. Computers are really good at things like calculating pi, but you need to give some kind of program or some specific instructions about how to do that. I'm not going to test this now, but I'm pretty sure if I ask Siri to calculate pi, she's going to be a bit confused. Even though she's supposed to interface with people. Certainly if you just type in calculate pi in Python, you're going to get some, the computer's not going to do that for you. But this is something like the first 1,000 digits of pi here, no problem for a computer. That can be calculated in fractions of a second. So it's a task that can be done very nicely, but you have to tell the computer the recipe or the instructions in a clear way about how to do that kind of task. And there are other things that computers aren't necessarily good at, and sometimes that can be related to problems of something that's either can't be solved or requires just too much power, too much computing power to deal with it. So here we have one of the biggest supercomputers in Finland, the SISU system, managed by the CSC, the supercomputing group. It's pretty powerful, 40,000 cores, a lot of RAM, but you can easily come up with problems that this system can't handle. If you ask it to calculate using some climate model, what is the variation in temperature at a 1 meter scale across the city of Helsinki? That's simply too big of a problem to be calculated. Maybe let's make it the whole country. But if you're calculating the temperature at 1 meter increments across the whole country, it's just such a large calculation, even a computer like this simply can't handle it. So there are things where obviously we have limitations, and even in our lifetimes we've seen what could be done by a computer has grown tremendously, but there still are things we can't do. Now we can talk a little bit about what is a program, and here we have a couple examples of some programs. So if you're really super old school, like born in the 1950s. I don't think we have anybody that's quite of that vintage. This is how programming was done back in the 1960s, which is with these punch cards in Fortran, where you would literally punch out little spots and you'd plug your card into the computer. It would read through there, and where there was different things punched out, it would do different operations. And fortunately, we don't have to do things that way anymore. But that was a program back in the day. It was a big stack of these punch cards, and you really didn't want to drop that stack of punch cards. And we have beneath that some Python source code, and it doesn't really matter what this does, just to kind of give you an idea again of what modern programming looks like. And even this is maybe not quite cutting edge Python, but it's some idea of what we do now, which is to type things into a program, save it, and run it. It's a lot easier than dealing with punch cards. In terms of what the program itself does, well, this is the detailed list that the computer needs to do whatever the task is you want it to do. So you have to tell step by step exactly what the computer should do. And so if it's calculate pi, you need to tell what should you do to get to this calculation of this number you want to know for some reason. And the program can be changed, can alter what the computer does when it is executed. Certainly you're going to be changing a lot of your programs. You'll make mistakes, and you'll go back and then try to fix the mistakes you've made to make sure the program does what you expect it to do. And the name software is just simply another name for something like a program. If you want to feel better about what you're doing, you can say, oh, I was writing software today. Maybe it makes you feel a little bit more important. As far as programming languages go, well, it's not so different from spoken languages that we use to communicate. This is our way to talk to the computer. If I want to talk to Henrikki, I can speak English. If I don't want to communicate very well, I could try and speak Finnish. But when I want to talk to the computer, I have to use the language that the computer understands. And so in that case, it's a programming language. And this is how the computer and I might have our conversation. I guess it'll be sort of one-sided, but
kind of different programming languages are like different spoken languages.
Yeah.
So English, Finnish. So basically, we have Python, Java, and so on. So
yeah.
they have we do things like I want to print something on the screen. So the meaning, like what I want to do, is the same, but with different languages, I just say it to the computer in a little bit different way. Yeah. So it's really similar.
Yeah, and it's just the same as, you have certain actions you want to do in your life. I want some ice cream, and you sort of can say that in English, and here in Helsinki you could say in English or Finnish or maybe even Swedish if you're lucky, and end up with some ice cream. So just a way of communicating. And the programming language is just a list of instructions that are in a form that the computer can understand. So you can't just type in things like calculate pi in Python because the computer doesn't understand that. You have to give it the language that it's understanding. So, if you speak rapidly to me in Finnish, you'll get the same response the computer would give you if you type in calculate pi, and I'm just going to stare at you and do nothing. So in terms of the language itself, it's exact, it's unambiguous. You don't want to have any uncertainty in when you tell something to the computer. It shouldn't be doing a different action every time you tell it the same instructions. It has to be specific and exact in terms of what happens when you type in the same command. And we can use these fancy words like syntax and semantics. Syntax is basically just the format of the language that you use, and the semantics is essentially what the computer should do when you type something in. So if you use the command print, that's the syntax would be the word print, and the semantics would be that the computer would then display something on the screen. So we could take an example like this in Python. Printing hello world goes back a long time in terms of programming. But if you put this statement into a Python console, type in print, parentheses, quotation mark, hello, comma, world, exclamation mark, quotation mark, and then the other parentheses. That will be a complete command the computer would understand, and when you run it, well, what's going to happen? Yeah, right? Nothing surprising there, hello world will be displayed on the screen. And here, the syntax in this case, again, is print. Semantics means put something and display it on the screen, just like we said a moment ago. If we take another example and we say, all right, computer, I'm feeling good, let's pring hello world. What's going to happen in this case?
It will print an error.
Right. So here, we've given it a command it doesn't understand. Computer's going to say, I don't know how to pring something, and you'll get some kind of error message that, in this case, most likely will say some kind of syntax error telling you you've given me a command that I don't understand. And I don't have the copy of the syntax error that Python gives, but if you want to test this, you can go ahead and try to pring something.
And this is something that we will face plenty of times during the course, and something that we want you to learn is how to actually try to understand the error messages that you get, because that is something that really comes up all the time, even for us when we do, so it's really natural to have errors.
Yeah.
Excuse me.
Mm.
Last question. Are we using Python 2 or Python 3?
Python 3.
Yeah, Python 3. So yeah, we can talk about the history of Python 2 and Python 3 at some point, but yeah, we're doing everything Python 3. So here's another example of how to do something similar. This is MATLAB. Probably for those of you sitting in the audience who've never seen any MATLAB before, you can already guess what this command does. And here we're using disp. It's basically the equivalent of print, but in the MATLAB programming language. So again, you can think about the analogy between English, Finnish, other languages that are spoken. We get the same expectation that something should be displayed. On the left side, beneath the Python, we have a Fortran 90 program that does exactly the same thing. You can see it's a little bit more complicated. And then we have in C exactly the same command. All four of these will do the same thing in printing hello world on the screen, but they just have to be told to the computer in a slightly different way. And you can see perhaps now why we're teaching Python instead of C. Because, you know, that's...
So there you can see that, for example, comparing Python to C or Fortran, so the Python version is much more kind of easier to do and understand.
Yeah.
But what is kind of the trade-off here is that basically the more, so to say, complicated code you do, like C, it runs much faster on the computer. So when you execute some program, so with C that requires more code, what it gives you is fast, speed to execute things.
And yeah, these are all examples of things we can call high-level programming languages. These are programming languages that are meant to be understood easily by people. So something like print, you can understand pretty much right away what that's supposed to do. The computer itself uses things like assembly language that are not meant to be understood by people very easily, and we won't get into any of that stuff, but it gets kind of, well, it's not nice. We'll leave it there. All right, so the last thing we'll do before we take a break here is just talk a little bit about the strategy of how to write a program, because this is something that we'll come back to basically every week when you're starting to write your code, and it's good just to think about when you want to solve any kind of problem, these types of steps to help you solve it efficiently. You could jump right into things like writing the code without really thinking about what it's supposed to do, but you're going to end up wasting a lot of time because you're going to make a lot of mistakes. And this strategy is meant to kind of help limit the number of mistakes that you're going to make. So you can see we have 6 steps here. We're going to kind of go through what these 6 steps are to make simple programs, and we'll do it with an example of a naive American such as myself, coming from a country where temperatures are given in Fahrenheit rather than Celsius. And probably, I don't know, maybe some of you are familiar with Fahrenheit, but 70 degrees Fahrenheit is quite nice, very pleasant temperature. 90 degrees is hot, and 32 degrees is the temperature at which water freezes. Very intuitive. And, you know, working here, of course, I can't find temperatures in Fahrenheit on the FMI webpage, so I need some way to get this information I have, a temperature in Celsius, into a format that I understand, which is a temperature in Fahrenheit, and I think that I can do this with a simple program. And so the first step here that I have to come up with is just analyzing the problem. Before I can come to a solution, I have to think about what do I need to do. In this case, the problem's pretty obvious. I need to know a temperature in Fahrenheit because I'm too dumb to know what the temperature in Celsius means in terms of what clothing I should wear. Okay, that's the problem. And it's always good to think about this when you're going to start writing your own code. What is the problem I'm trying to solve? Then we've got specifications. We need to determine what kind of information do I need to know in order to solve the problem that I want to solve. And exactly how things are going to happen at this point doesn't matter, but I need to know what I will be working with. So what are the input values? In this case, it would be I'm going to have an input, which is a temperature in Celsius. The output value should be some temperature in Fahrenheit. And that's essentially all I want to do. I want to have some magic happen inside the computer to give me this temperature in Fahrenheit. The next step is to design the program. And this is something that I think is actually probably one of the most useful things to do when you're trying to write programs in the beginning. And that is to think through what is the actual structure of the program. In what order should I do the things I need to do in order to get what I want out of the program? And we'll mention this term probably a few times about writing things in pseudocode. This means basically just writing down in a language you're comfortable with what the program should do. And it doesn't have to be written in Python. It could be written just in regular spoken language or written language. And that could be things like, okay, well, step one is I should input some temperature in Celsius. Step two, I should calculate what that temperature is in Fahrenheit. And step three, I should print the temperature in Fahrenheit on the screen so that I can know, whether I should wear shorts or not when it's 5 degrees. So this is really getting into being a little bit more specific. We've defined the problem. Now we want to know exactly what are the steps to solve it. And once we have that, then we can basically just translate what we've written into Python. That step is really easy to do if you have the pseudocode. You'll be making some mistakes with syntax and things like that, but if you have a picture of what order do I need to do this stuff in, it's very easy to then just say, okay, well, I got to have some kind of input statement, then I've got to have a print if I want to display the temperature, I got to do some calculation. These two steps in here can save you a lot of time, especially if you do the pseudocode first. And I think probably all of us who've done Python programming before have skipped step 3 and just started right into step 4 and wasted a tremendous amount of time not realizing how you should actually set up your program, but just kind of jumping right into the typing up the code part. It's a big time sink. I've lost a lot of time with things like that.
Especially when you're doing a larger programs, then you really should sit down and think a little bit first.
Yeah. It's very tempting, especially when the computer's right in front of you, to just jump right into coding, but it doesn't work very well. So after you have written your code, that was the implementation, you can test it. And a good way to test your code is to take things like values that you know and see if you put in a temperature, for instance, in Celsius, where you know what the temperature should be in Fahrenheit, do you get the temperature out that you expect? If I put in 0 degrees Celsius, I expect to see 32 degrees Fahrenheit as the output from my program. If I put in 100 degrees Celsius, I expect to see 212 degrees Fahrenheit as the output from my program, because those are values that I know. Once I've tested the program and seen that it works for values within the range of things I'm considering, then I start to feel pretty good. Maybe it's a good idea to put a negative temperature in there just to see if a negative number causes a problem. There's lots of things like that, but a big part at the point you have your code is to actually test and see if it does produce results that you know it should produce if it's working properly. And then the last thing, part 6 here, is kind of, it's true to a varying degree to us about maintaining the program. If you're going to share your software, it's a good idea that you kind of keep up and take care of it. If things change, that some library that you're using in your software doesn't work the way it used to, then it's nice to update the software to keep it
one benefit of being open and publishing openly your software, for example, is the fact that maintaining the software is kind of a task that you wouldn't necessarily want to do. But if you kind of gather a community around your code, so you're not the only one necessarily that can actually start maintaining it, and it can actually start living its own life basically on the web.
All right, so those were our 6 steps for how to do a program, and I think I'm going to skip these questions and not make you suffer through having to maybe you can think back to yourself, do I remember what a computer is? Do I remember what a program is, and some of the steps? But at this point, we're going to take maybe 10 minutes?
Yeah, maybe 10 minutes.
10-minute breaks. So we'll come back at, let's say 10:35, and we'll continue on with the second part of the...
Yeah, so next we will go through, see a little bit of practicalities and how do we actually work during the course.
Yeah. So we'll see you in 10 minutes.